Hi, everyone. I'm Randall Ritzak. I'm part of the organizing team for the Future of Electrification on behalf of the ZAPI group of companies. I'd like to welcome you to the session. Please remember that the session is also being recorded and it will be available to watch on demand following this session. If you have any questions during the presentation, please add them to the Q&A. You can find that tab to the right of your screen along the top area. Note that any questions that you put in there will be sent privately for us to get to at the end of this session presentation. So with that, I'd like to introduce our speaker. I'd like to welcome Florian Pauli from Schabmüller. Florian is a product development engineer at Schabmüller, and he'll be speaking to us today about scalable models of induction machines to predict motor performance. Welcome, Florian. Please take it away for us.
Thanks for the kind introduction. 1 second. So, as you just said in your kind introduction, I will talk about utilization of scalable models of induction machines to predict the motor performance under varying thermal conditions. Oops, sorry. First of all, I'm working for Schabmüller. We are producing electrical machines, permanent magnet synchron machines, and what today's presentation will be about induction machines. We have a large product variety and a large product range for both of these machine types. For induction machines, it's 9 different series. Series of induction machines is defined by the stator diameter of the machine, which ranges from 166 millimeters to 300 millimeters for our products. We can produce a large number of variants by adapting the actual length of these machines and the winding configurations. As an example, the actual range ranges from 50 millimeters to 120 millimeters for our smallest machine series, the TSA 106. When this nomenclature, the 106 stands for the outer diameter in millimeters, and from 100 millimeter to 300 millimeter actual length for the TSA 300. Our targets when making offers to the customer are to have computational models which are precise in predicting the performance for all of these different machines. And we also need to be able to make rapid calculation. This enables our engineers or application engineers to rapidly respond to customer requests, and reliable models are key to offer the optimal motor for given customer application. And when it comes to designing a vehicle, then an accurate prediction of the motor parameters leads to high confidence in the choice of the correct inverter. So what's our goal? Our goal is to take the requirements from our customers, use our models, which can be regarded as kind of an electric digital twin of the electric motor, and then have a precise performance prediction. For the outline of this presentation, I first will talk about some general basics of scaling electrical machines. What are the what's the general scaling approach, what are other limitations of the machines. Then I will come to our measurement setups and how we measure torque, speed, and temperature of electric machines. And then I will introduce the parametrization approach. And yeah, in the end, there will be a performance analysis of these computational models. So how does scaling affect the performance of electrical machines? We take, to answer these questions, we take a simplified approach where we only consider the active part of the machine. The active part means, yeah, only the fraction of the length which is covered by the rotor and stator iron lamination, which kind of looks like this in the figure down here. We have some simplifying assumptions. One is we want to keep the losses over the length, or the losses per length of the active part the same, and we want to keep the magnetic field distribution in the stator the same. And this leads to the to the conclusion that we must keep the current density inside our machine the same. Why is that so? Considering the losses per length, this can be motivated if you take a look at the right figure right here, where we have one slot with a coil with a winding number of 4 and one with a winding number of just 2. So to keep the losses the same, we need to keep the loss in each wire, so in each circle on this diagram here the same. And to do this, we need to keep the current in each of these wires the same. If we just keep the overall current through the coil the same, we would end up with a current density twice as high in the left coil than in the right coil, because in the left coil, yeah, the current is distributed over fewer wires. And as the current is directly linked to the produced copper losses, yeah, to keep the losses the same, we need to keep the current density the same. For the magnetic field distribution, yeah, it would be beyond the scope of the presentation to explain this, but it's also kept the same if we take the same approach. So now if we assume a constant current density, what happens if we, if we double the length of the electric machines? For extra scaling, it is known from basic machine equations that the torque will be proportional to the length. The voltage will also be proportional to the length, and the current will remain constant. So if we do that and take a look at the torque speed map, we see that we will double the torque when doubling the length. But if we take a look at the current voltage map, we will see that we need the same current, but twice the voltage to reach this operation point. So when rewinding the machines, so basically varying the number of turns, the torque will remain constant by these operations. However, we receive lower current but higher voltage. So this is basically the way our engineers use to adapt machine requirements of voltage and current to the inverter of electric vehicles, for example. So the machine is limited by several factors. One is the supplying inverter, which offers a maximum voltage and current by overheating and by magnetic saturation. So what does it mean if we have a limited current and a limited voltage, considering the effects of scaling I just showed you on the slide before? Basically means if I double the length of the machine, and this is my the operational limits of the original machine, I will double the the torque limit. Why is that? Because the torque limit in this region, the torque is limited by the maximum current. So I have to keep my fingers off the mouse, I think. And if I double the number of turns, I will receive quite similar operating behavior as I need now less current to produce the same current density, and with the same current density, I can produce the same torque. However, the machine with a doubled number of turns is significantly higher saturated and also significantly more prone to overheating. So while the magnetic utilization can just be considered with electromagnetic modeling, we need to make some thermal investigations to find out more about our thermal limits of our machines. So that's where we come to the next chapter, where we take a look what we're doing to our machines on the test bench. When our machines are mounted on the test bench, it typically looks like that. That's a typically torque test bench where there's a load machine on the left and the device under test on the right. And the load machine provides a certain torque or requests a certain torque, which has to be provided by the load machine if you want. And this is how we can characterize. And if we then measure current, voltage, the torque, and the speed, we can more or less fully characterize the mechanical and electrical outputs or parameters of the machine. What's also done more or less and is more or less state of the art is measuring the stator temperature or the binding temperature of the machine. We developed a new approach where we can also measure rotor temperatures. It's not always or usually not done because it's quite cost expensive. But with our procedure developed Schabmüller, we use a wireless low cost rotor telemetry. And if customers require thermal data about the rotor, we can perform these for prototypes on our test bench. How does this this measurement setup look like? We have two sensors which are transmitting in the rotor, and we have or one or two. We can also measure it with one sensor, and we have a receiver in the stator. And there are several possibilities to place these sensors on the rotor. Here you can see one sensor which is glued to the surface, and one it's where we have produced a little hole there. so we can measure the temperature inside the short circuit ring of the rotor. Yeah, but during our measurements, we have seen that we have very similar temperatures for both of these setups. And thus, of course, the sensor which is glued to the surface is preferred as it's, of course, easier to place there. And also, we don't affect the rotor slip ring by producing a hole in there. So the advantages of the rotor temperature measurements are that we no longer need to take educated guesses on the bar temperature. This leads to a better prediction of the thermal machine limits, and it also leads to a better prediction of the machine's performance, considering efficiency, maximum torque for a given current, and breakdown behavior. Why does the rotor have an influence? Here we can see the breakdown curve of an induction machine, torque over speed, for a fixed voltage and a fixed frequency. And for cold rotor, we have smaller resistance, rotor resistance, and then we have a steeper characteristic here than for a warm rotor. And if we take a look how this affects the entire torque speed range we can cover with our machines, yeah, we see that the in this area, the maximum speed that can be achieved at a given torque is shifted by up to 5%. Yeah, this is because a warmer rotor loads to an increased slip, and this slip is caused by the additional losses we produce. Yeah. So some exemplary results from our rotor temperature measurement show why it's not so good, or not always so good, to take educated guesses from the stator temperature. Here we have measured the rotor temperature for a machine, for an induction machine with an outer diameter of 170 millimeters and an axial length of 50 millimeters. And in steady state, we can see that the rotor temperature is more or less constantly about 15 K higher than the stator temperature. Even though only 15% of the losses accrue in the rotor at this operating point. Why is that so? Why is the rotor significantly warmer? Yeah, because it's placed inside the stator. As you can see in this section here. And yeah, the stator dissipates its heat via its surface of the housing here. And the rotor, the heat of the rotor is dissipated by a small fraction through the shaft, and also via the stator, and then by the housing. And between the stator and the rotor, there's of course the air gap, and this air gap acts like an insulating layer, and that's why the rotor is significantly warmer in steady state, even though it just produces a fraction of the losses. So then we have taken another operating point where we've applied quite high torques. You can see that stator and rotor are rapidly heating up. However, in this case, the stator temperature is yeah, even a little bit lower than the rotor temperature, and that is caused, yeah, by the fact that there are thermal capacitances that need to be heated up, and that might take some time. You can see that also for the sensor, which was not placed directly at the windings, but at the housing. it takes some time until it even starts to warm up, and then it significantly lags behind. So it depends very much on the operating scenario, if the rotor is warmer or the stator is warmer, and how large the temperature difference between those two components is. So for our parametrization approach, we want to have an accurate model. We want to have, of course, a limited parametrization effort, as we have a high number of variants, and for our computational models, and we want to have scalability of these computational models, meaning that we can do what I just showed you in the beginning, applying these scaling laws on a computational model and get satisfying or good results considering the performance, without having to rely on measurement data for each and every time we change the winding configuration a little bit, or we change axis scaling. So we choose a hybrid approach. We take a physical model of the machine, but it's also a data-driven model, in terms that there are a certain number of parameters that are adapted based on measurement data. The physical approach enables us to achieve the scalability of the model, and the parametrization based on measurement will increase our accuracy. The required data we need is the stator and rotor geometry and the winding configuration, which we of course got since we are building the machines. And we need mechanical and electrical measurement data, as well as rotor and winding temperatures, which we can get from our test bench measurements. So we need a robust automation process that yields such a scalable model. In our model, we have identified 8 parameters that need to be adapted. And in general, you can say that a large number of parameters makes an optimization process less robust. To overcome this, or to make it more robust, we have identified 4 parameters pairs, which can be adapted stepwise, and will not have, or will only have, a negligible influence on the parameterization step we did before. And so we achieved to have our scalable model, and then we will just need one set of measurement data per machine series, per outer machine diameter, and then we can parameterize the model and use the scaling laws to predict the motor performance for more or less each configuration of this machine series. So now I come to the performance analysis of our computational models. At first, we measured no-load curves, which is more or less to see for ourselves if our model has a good performance, because as a customer, you will usually not be so much interested in the no-load. We can see that the fit of stator and rotor related parameters yields to a very small error over the whole operating range. can see here on the x-axis the voltage in volt, on the y-axis, other way around, on the y-axis the voltage in volt, and on the x-axis the current in amperes. And the measurement was performed for a whole variety of frequencies. And we can see that for each frequency, our voltage error is within 0.2 volts, which is quite satisfying. So then we've taken load curves and we performed the fit for a TSA 106/65, meaning a machine with 106 millimeters outer diameter and 65 millimeters actual length. In this example at 80 Hertz. And here you can see the simulation data of the best fit measurements. This measurement data is obtained by having the machine on the test bench and submitting it to a given frequency, and which is 80 Hertz in this case, and ramping up the torque. And here the cosine phi, the current, and the slip are displayed. And this is still done without rotor temperature measurement. And we can see that we already have a high accordance of measured and simulated data. However, cosine phi has a relative error of about 5% over the entire torque range. So then we applied, or we did our first tests with rotor temperature measurement. And this time with a different machine with 170 millimeters outer diameter. We can see that the relative error, or the overall error we had between measurement and simulation is significantly smaller, for almost each operating point below 1%, if we take this approach. Here you can see the comparison between the two measurements with rotor bar, without rotor bar temperature measurement. We already yield good results, but with rotor temperature measurement, we can even fit the simulation data, even fit the measurement data better with our simulation. Why is it so? During the measurement, we try to keep our winding temperature more or less constant, in this case between 100 and 110 degrees. However, the measurement run takes some time. And during that time, we will, it almost certainly happens that the machine will become hotter than these 100 and 110 degrees, and then we need a cool down phase. And this procedure leads to a more or less stable winding temperature. But as said before, the rotor temperature is nothing more than a guess. And we can see that in this plot, or in this example, the temperature range from 199 to 124 degrees, while the stator temperature is more or less constant. And therefore, knowing and considering the rotor temperature in the parametrization approach will, of course, yield a more suitable and more reliable model. So as of now, we have just seen the results of the parameter fit. And now we will take a look at what happens if scaling laws are applied. And this means we take the parametrization we achieved for the in this case TSA 165, and applied to the apply scaling and rewinding, and use it for the TSA 10690. Yeah, and we can see that the scaled model also achieves a very high accuracy. Typical errors are below 2.5%. At very low torques, the deviation that occur can be a little bit higher, but yeah, overall we have an accurate current prediction, and this leads to a high confidence in inverter choice, and this then leads for our customers to a high confidence in vehicle performance. So we've also done this for a downscaled machine, which is also only 50 millimeters long. We have similar results here. The errors are a little bit higher. Yeah. So to sum everything up, I've introduced the scalable model of induction machines, and we are using a parametrization approach which enables precise prediction of the machine performance. If we take temperatures, especially the rotor temperature, into account, we can further increase the accuracy of our models. And as mentioned before, accurate models lead to a high confidence inverter choice. So we've already produced a digital twin for our electric behavior. Our next steps would be to have a thermal model of the machine, which would enable us to predict the machine's thermal behavior, the temperatures inside rotor and stator, if the machine is subjected to a certain operational scenario, like a drive cycle or something. Yeah. So that's it. Thank you for your attention.
Thank you so much for that, Florian. Really appreciate the presentation. I think we have a couple of questions. So if anybody has any questions for Florian, please add them to the Q&A button. You'll find that at the top right corner of your screen. Florian, just to get you things kicked off, there's a couple questions here. One question I have is, can you talk a little bit more about the rotor temperature measurement and the availability of the capability across the Schabmüller product line?
Yeah. So it's not the right slide, but this is. And yeah, so we have developed this procedure because, yeah, as I've shown in the presentation, the rotor temperature is not, constantly linked to the stator temperature. And yeah, we have developed a methodology where we can, more or less easily apply this for all our induction machines. And on customer request, this is available for induction machines from Schabmüller from now on. On our test bench. So it's a thing we do during prototype production.
Thank you for that. A couple more questions from the audience here. How is your experience with the wireless method on PMSM machines?
Yeah, we've started with it, but we have not implemented a suitable process for it yet. We have done it for one example, and hopefully sometimes we will extend that to PMSMs.
Great, thank you. There's another one here. To what rotational speeds is the wireless method limited?
To be honest, I cannot tell because our machines turn up to maybe 4,000 or 4,500 RPMs, our induction machines, and it has not been an issue there.
Great, thank you. Another one here, Florian, from your model and simulation capabilities, are you able to estimate motor lifetime expectations in specific ambient temperatures and working cycles?
So I have an approach for that, or we have an approach for that, but it's not like a safely implemented process at Schabmüller yet, I think. You mean like if the machine is subjected to certain temperature changes during its operation time, correct? Yeah.
Great. Okay, thank you. One looks like probably a final question here. May inverters only supervise the stator winding temperature? Do you also take this rotor temperature into the inverter to apply a derating strategy?
This is currently only done on the test bench. So on the test bench, we don't have derating strategies or anything because we don't have these. The rating strategy is a protection for the equipment, and that's not transmittable to the test bench. I think it's just So to be clear, this kind of rotor temperature measurement is currently only for prototype production on the test bench.
Great. Okay. Thank you. Thank you, Florian. I think that's the end of our formal questions. Anything else that you'd like to add before we let the audience go?
Thanks for having me.
That's great. Thank you, Florian. So with that, thank you, Florian, for your presentation. Just a reminder that Florian's presentation is going to be available on demand through your portal after the session. And with that, we'll let everybody go. Please feel free to join the next sessions from the lobby. And thank you again for joining us today.